Okay, no problem. Let us proceed. Yes, are you able to see my shared screen?
Yes, sir.
Yes, sir.
Yes, sir.
Now today we will talk about matrix exponential, and then we will use this and Jordan Canonical form to solve system of linear differential equations. Okay, so suppose first we will define matrix exponential. So we have a matrix. Suppose now I fix my field to be C. Let A be a matrix in n cross nf. We can define the exponential of this matrix e to the power a to be I plus a square upon 2 factorial plus and so on. Just like the exponential of a number is defined, matrix of exponential is defined on the same way. E to the power a means I means identity matrix of the size n plus a square by 2 factorial plus a cube by 3 factorial and so on. Does it make sense? Now the one problem is that this is an infinite series and you will make a square cube of the matrices and go on doing the sum. Then will it converge? So the answer is yes. There are methods to show that yes, you will get a finite number here, finite matrix here. So we will not bother about it, whether it converge or not. It will converge, there are results. Okay. For example, suppose I take a matrix A to B, A1, A2, AN in the diagonal. So it is a diagonal matrix. Other entries are 0. Then what will be its exponential? So let's try to do it. So the exponential of A is equal to In plus A square by 2 factorial plus A cube by 3 factorial plus and so on. Okay. So when you will put the value, the square of this matrix A square will be A1 square, A2 square and AN square in the diagonal and other entries 0. The cube of this matrix will be A1 cube, A2 cube and AN cube and the other entries will be 0. Do you agree with me?
Yes, sir.
तो इसको अगर हम लोग लिखेंगे तो क्या होगा, हर एंट्री में, हर डायगोनल एंट्री में क्या होगा, 1 plus A1 square by 2 factorial and so on.
Yes.
Then the second diagonal entry will be 1 plus A2 square by 2 factorial and so on. ऐसे ही होगा
Yes, sir.
हम करने पे. And on the same way when you will go to AN, then it will be 1 plus AN square upon 2 factorial plus and so on. And the other entries will be 0. Do you agree? So it is nothing but
Yes, sir.
e to the power A1, e to the power A2 up to e to the power AN and the other entries are 0. Is it okay?
Yes, sir.
Yes, sir.
Yes. Once again see it. Matrix exponential we are defining. Suppose A is n cross n matrix. The matrix exponential is defined on the same way as this exponential of a number is defined. E to the power A is equal to In plus A square by 2 factorial plus and so on. So for example, I take a diagonal matrix A1, A2, An and I determine its exponential e to the power A. Then this turns out to be e to the power A1, e to the power An, e to the power An, e to the power A1, e to the power A2 up to e to the power An in the diagonal and the other entries are 0. So it is again a diagonal matrix. Suppose, yes, let me. Another example. Suppose A is a nilpotent matrix of index k. What does it mean? It means that a to the power k is zero matrix, but a to the power k minus 1 is not a zero matrix. Then do you know what will be a to the power a? It will be 1 plus 1 mean identity plus a square upon 2 factorial plus and so on up to where? A to the power
K to the power
k minus 1 upon k minus 1 factorial. So it is easy to determine this matrix exponential for an nilpotent matrix. Next example. In a particular case of a nilpotent matrix, let us take this matrix JK0, means elementary Jordan matrix of the size k cross k. So what is its entry? Diagonal entry 0, lower diagonal entry 0, above the diagonal entries are 1, and the rest of the entries are 0. Do you agree? Now let us determine its exponential. So we want to determine e to the power jk0. What will it be? This is a k cross k matrix. Okay, jk means k cross k matrix. So identity of order k plus jk0 plus jk0 square upon 2 factorial plus and so on. See, this is also a nilpotent matrix. Do you know what is the square of jk? Do you know what is the square of this matrix? Diagonal entry 0, upper diagonal entry again 0, and just above that all the entries will be 1. I think if I do it for some particular k value of k, then it will be easier to understand for you. Let me take it 4. Let me take it 4. Okay, so let me take it 4. J40. So this matrix will be 4 cross 4 matrix 0 1 0 0 0 0 1 0 0 0 0 1 and 0 0 0 0. I think it is okay now. And when we will do the square of this matrix, then what will it be? Let me write it again. G40 square. So now you can calculate very easily. Its square will be 0 0 1 0 0 0 0 1 0 0 0 0 0 0 0 0. Do you agree with me?
Yes, sir.
Yes, sir.
What will be its cube?
Yes.
What will be its cube? And what will be its fourth power?
Zero
Zero
matrix.
matrix.
Yes, its fourth power will be a zero matrix of 4 cross 4. So you can easily determine its exponential e to the power j40. E to the power j40 will be a matrix of the form. So identity matrix will give you what? Identity in the diagonal. So the final matrix will be 1 0 0 0 1 0 0. In the diagonal, identity matrix will give you 1. Now see what is J0. J0 is just above the diagonal entry is 1. So when you will sum J0, you will get 1 here, 1 here, and 1 here. And then J4 square, J40 square by 2 factorial. J40 square by 2 factorial means you will divide each entry by 2. So it will become 1 by 2 and 1 by 2 here. And J40 cube by 3 factorial. So this 1 by 3 factorial you will divide here. So 1 by 6 will come here. and the rest of the entry will become 0 because j4 to the power 4 is 0. So this is the exponential of this Jacobian matrix. So if you guess for in general Jacobian matrix e to the power k0, then what will it come? Again diagonal entry 1, above the diagonal entry again 1, entry above that will be 1 by 2, 1 by 2, 1 by 2, above that 1 by 6, 1 by 6 means 3 factorial and so on, and so on it will go. The last entry here will be 1 upon k minus 1 factorial. Do you agree? And the rest of the entry will be 0. Okay, let me
Yes,
write
sir.
it. It is not very good. So this will be 1, 1, 1 by 2, 1 by 3 factorial up to 1 upon k minus 1 factorial, and the diagonal entry will be 1 throughout. Just above the diagonal entry will be 1 throughout, and above that entry will be 1 by 2, 1 by 2, 1 by 2 in this row, 1 by 3 in this, and then at last 1 over k minus 2 factorial, and in the last entry that will be 1 upon k minus 1 factorial. Do you agree at this point on the same way?
Yes, sir. Yes, sir.
Yes, sir.
Is it okay? Diagonal entry is 1, above diagonal entry is again 1, entry above that will be 1 upon 2 factorial, above that 1 upon 3 factorial, and so on. It will go on. So in this way you can determine the exponential of this type of matrix very easily. Okay. Yes. Now there are some results for this exponential of matrices. Before that, let me define. I think you all know what do we mean by system of linear differential equation. So by a system of linear differential equations with constant coefficient we mean the equations of the form x1 dash is equal to a11 x1 a12 x2 plus a1n xn. Similarly, x2 dash is equal to a21 x1 plus a22 x2 plus a2n xn. What are AIs? Aij are the constant coefficients from the field. So you may take it field of complex number n1 x1 plus up to ann xn. Is it okay? Now we can write this whole system of equation, differential equation. So what is x1 dash? X1 dash mean d by dt of x1. Similarly, this is d by dt of x2, and similarly this is d by dt of xn. So x1, x2, xn are variable. Aij's belongs to R or C. C, let us take C. Now I will write it as take x to be x1, x2, xn. Consider a matrix A to be Aij, n cross n matrix, and by x dash I mean x1 dash, x2 dash mean derivative of x, xn dash. Then the system of linear equation 1 can be written as 1 can be written as x is equal to x dash is equal to a into x. Do you agree? So this is the matrix form of this system of linear differential equations with constant coefficient. Do you agree?
Yes, sir.
If
Yes, sir.
anyone
Yes, sir.
any confusion at this point, then please ask me, because we are going to use it throughout the lecture. No confusion? This is a system of linear
No, sir.
differential equation and I write it in the matrix form. For example, for example, suppose I have a system of linear differential equation. X dash is equal to x1 plus x2. x2 dash is equal to minus x1 plus 3x2. x3 dash is equal to minus x1 plus 4x2 minus x3. So we can write it as x1 dash, x2 dash, x3 dash as a one vector. This is equal to a matrix of coefficients. So coefficient is 1, 1, 0, minus 1, 3, 0, minus 1, 4, minus 1 into x1, x2, x3. This is the matrix form of this system of linear differential equations with constant coefficient. Okay. Now there are some facts.
Sir,
Yes.
sorry for the interruption. Sir, are you taking only homogeneous system of?
Yes, yes, yes.
Differential? Okay.
Yes. Now there are some facts about exponential which I will tell you, and I will use this exponential to solve this system of equations. Some facts. These are the theorems, these are the results which I am going to use, but we are not going to prove it. Fact number 1, let A and B are two n cross n matrices over C such that AB is equal to B, means these two matrices commute. Then the exponential of A plus B is equal to exponential of A into exponential of B. Second thing, for any A in M n cross n C, e to the power A is invertible and its inverse is e to the power minus A. So it means take any matrix, whether invertible or not, its exponential will always be invertible. The fact number 3 is, if you take, let A is in this, the column vectors the columns of matrix e to the power Ta forms a basis for the vector space of solutions of the differential equation x dash is equal. So this is the system of linear differential equations with constant coefficient, homogeneous, and the solution of this is e to the power ta. So that is the use of matrix exponential. Do you get my point? What is the
Yes,
use
sir.
of matrix exponential? This exponential of this matrix e to the power ta is actually the columns of this matrix will give you the linearly independent solutions of this system of differential equations.
Sir, what is T here?
T is a variable. We'll see here. We have taken x1 to be a function of t, x2 to be a function of t, and xn to be a function of t. Okay. So independent variable t, xi's are the function of t. Is it okay?
Yes, sir.
Yes, sir.
Now, so what we are to do is that we are to calculate this e to the power ta. And if we calculate e to the power ta, we will get n linearly independent columns because e to the power ta is an invertible matrix. So we will get n linearly independent solutions. So we can write the whole general solution as a linear combination of these column vectors. So we will get the whole solution of this system of differential equation. Okay. Now, fact number 4, or result number 4. If you take e to the power p a p inverse, then it is same thing as p e to the power a and p inverse. And it is actually quite easy to prove because if you will write, if you will expand it, you will get the same thing. This is 1 plus p inverse ap plus p inverse ap square upon 2 factorial plus p inverse ap cube upon 3 factorial plus and so on. And when you will expand it, you will have I plus P inverse AP plus P inverse A square P upon 2 factorial plus P inverse A cube P upon 3 factorial and so on. So you may take 1P here and the expression inside will be plus and so on and 1P here. So it is nothing but P e to the power A P inverse. Is it okay? So if you will make a conjugate of this matrix A, then e to the power that conjugate will be the conjugate of e to the power A. Sorry, it should be inverse here and P here. Correct. Is it okay now?
Yes,
The
sir.
same mistake I did here.
Yes, sir.
This is this P inverse P. One more correction. Is it okay now?
Yes, sir.
Yes. Now see, what we can do is that and fifth, we know that if we are in algebraically closed field and given a matrix A, we know that given A in M n cross n C, we have an invertible matrix P such that this is equal to the Jordan form of A. By J means Jordan form of A. Okay. You know it? Now see, this Jordan form has two parts. Jordan form has two parts. One is the diagonal matrix and another form is nilpotent matrix. Nilpotent and diagonal matrix. That is called the Jordan-Chevalier decomposition. Do you agree?
Yes, sir.
Yes, sir.
Just remove the diagonal part from the Jordan canonical form and write it as separate matrix, and whatever remains write it as a separate matrix. You will add it, you will get the complete Jordan form. So this is a diagonal matrix and this is a nilpotent part of that Jordan canonical form, and the property of these two is that these two matrices commute. If you will multiply these two matrices, these two matrices will commute. Is it okay?
Yes, sir.
Now, if I determine e to the power this AP, then what will we get? We will get e to the power dA plus NA. And the facts which we have done previously, by that fact we can write it as dA e to the power NA. And we have seen that for nilpotent matrix, then determining the exponential is an easy work, and for diagonal matrix, determining exponential is an easy work. So we can determine this exponential. Now we can change it and write it as P inverse e to the power A P to be e to the power dA e to the power NA. Do you agree? So it means we can determine e to the power A to be P e to the power dA e to the power NA P inverse. Okay. So this is the method of determining the matrix exponential. So using Jordan canonical form, you can determine the matrix exponential. So it means you can solve a given system of linear differential equations with constant coefficient and homogeneous. Is it okay? Are you able to understand?
Yes, sir. Yes, sir.
So we will do one example for it. So why not we take this example which we have stated here, this example. So let us write it again. So we'll do example for it. Method is clear. What we will do? So suppose we have a system of linear differential equation given by x1, x2, x3 dash 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 is equal to a matrix 1 1 0 minus 1 3 0 minus 1 4 minus 1 into x1, x2, x3. See, this is the same example which we have taken. 1 1 0 minus 1 3 0 and minus 1 4 minus 1. So this is our matrix A. This is our matrix A. So what is the solution of this system of equation? The solution of this system of equation is e to the power ta, and that is what we want to determine. We want to determine e to the power ta. Is it okay? The columns of matrix e to the power ta will give you three linearly independent solution of this system of equation. So the general solution will be the linear combination of these three linearly independent solutions. So let us determine e to the power 3a. What we will do is that we will determine the Jordan canonical form of A. So first step is step 1, to determine Jordan canonical form of A. So we will determine the characteristic polynomial first. So characteristic polynomial of A is equal to, see this matrix. So this is the determinant of 1 minus x, 1, 0, minus 1, 3 minus x, 0. Please start calculating it and tell me the answer very fast so that we can complete it easily. What will be the determinant of this matrix? Yes. Let us open with this first row. This is 1 minus x. Yes. And then determinant of this 3 minus x into minus 1 minus x plus 1 times determinant of a matrix and C 1 times. So let me write it directly. Tell me the answer if you have solved. So this is 1 minus 1. So this is 1 plus x. This will be minus 1 actually. 1 plus x and 0. Yes, it is 1 plus x. Am I correct?
Sir.
So this is, yeah, this is also 1 plus 1 minus x. That's it. Okay, so what is the determinant here? So this is 1 minus x, 3 minus x, and 1 plus x. Yes, and minus will come out, and this is minus 1 plus x. So you can take 1 plus x common. So this is 1 plus x common. We have minus, so why not take minus 1 plus x common? So this we have 1 minus x, 3 minus x plus 1. Am I correct?
Yes, sir.
So what is this? This is minus 1 plus x and 1 minus 3x minus x plus x square and plus 1. There will be 3. Yes, 3. This is 3 minus x minus 3x and x square. Yes, I'm right. So this is 1 plus x minus, and this is x square minus 4x plus 4. So it is minus 1 plus x and x minus 2 whole square. So this is the determinant characteristic polynomial of this matrix. Now what is the minimal polynomial for this matrix? Minimal polynomial. So the possibility for the minimal polynomial is 1 plus x and x minus 2 or 1 plus x, x minus 2 square. These are the two possibilities for the minimal polynomial. If this will be the minimal polynomial, it will be diagonalizable. If this will be the minimal polynomial, it will not be diagonalizable. So the given matrix A is 1, 1, 0, minus 1, 3, 0, minus 1, 4, minus 1. So let us determine it. 1 plus A into A minus 2i.
So,
Yes.
so minimal polynomial will be minus of 1 plus x. X minus
It's okay. Monic, if you will take monic, then you can remove this minus. If you want to monic characteristic polynomial also, you can remove minus. Yes, write minus here, it will not affect the things. Okay. So what is 1 plus a? 1 plus a is a matrix. So we will add 2, 1, 0, minus 1, 4, 0, and this is minus 1, 4, and 0 here. And a minus 2i. So a minus 2i is minus 1, 1, 0, minus 1, 1, 0, and minus 1, 4, minus 3. And as you can see, when we will take the product, this product is non-zero. See, just calculate the first row, you will get non-zero entry. Am I correct? So this is not equal to 0 matrix, 3 cross 3. So this is not the minimal polynomial. So the minimal polynomial here is what? Minimal polynomial of this matrix A is minus 1 plus x minus 2 whole square. So this is the minimal polynomial, and you know that when you will write the Jordan Canonical form, the minimal polynomial is of degree 2, so there will be a block of degree 2. So there will be a block of degree 2 for this eigenvalue 2, but its characteristic polynomial is same, so there will be only one block here, and the same situation is for this block. So this sum, one block of size 1, because here the power is 1 and the eigenvalue is minus 1. So this is the case. So the Jordan Canonical form for this matrix is this. Do you all agree? So if you
Yes,
write
sir.
matrix form, so it will be 2, 2, 1, 0, 0, 0, 0, 0, and this one. This is the Jordan Canonical form JA for this matrix.
Yes, sir.
Okay, now the problem is to determine the P. So step 2 is find P such that this PAP inverse is equal to JA. Okay, now the thing is that when you take any matrix A, then actually the P is the basis vector, Jordan basis vector. The columns of P are the Jordan basis vector on which this Jordan canonical form is attended. Okay, so it simply means that we need to determine the Jordan basis vectors. Now see, what is the minimal polynomial for this? X plus 1 and what was another term? X minus 2 square. X minus 2 square into minus 1. Okay. Even if you remove this minus 1, it will not affect our calculation. So I'm just leaving this minus 1 here and I'm doing calculation with this thing. So primary decomposition theorem says that you have this space C3 can be written as a sum of kernel of x plus 1. So x is a plus I, direct sum kernel of a minus 2i square. You can write it like this. So you need to determine a basis from here and here. So you will determine a basis for this kernel of a plus I and basis for kernel of a minus 2i square, and that basis, when you will combine, you will get the basis of C3. So here the basis which we will determine and here the basis which we will determine. Let us calculate it. Let us calculate this basis. So what is a plus I? We want to determine the kernel of a plus I. So the kernel of a plus I means those x in C3 such that a plus I into x is equal to 0. So what is a plus I? So a plus I is the vector which we have calculated. A plus I is equal to 2, 2, 0. See here, a plus I is 2. A plus I 210. Yes, this is 210. 2 1 0. Take your copy and pen, and you also calculate me, so that if I make any mistake, then you can tell me the mistake. Okay, and then let me write A here, and then the calculation will become easy. So the matrix A is 1 1 0 minus 1 3 0 and minus 1 4 minus 1. So A plus I is this 4 and 0 0 minus 1 minus 1 4. Do you agree?
Yes, sir.
So we can reduce this matrix by row reduction. So it will become 2 1 0 and minus 1 4 0 0 0 0. We can make this minus 1 to be plus 1 like this by multiplying second row to minus 1, and then again you have you can make this 1 by 2 0 and 1 minus 4 0 0 0 0, and you can make this 0 how 1 by 2 0, subtract it row 1 from the row 2 0, and minus 4.5 0 0 0 0, and you will reduce it again, and you will have 1 half 0 0 1 0 0 0 0. Okay, so the solution for this system of linear equation and solution for this system of linear equation, see, linear equation, not differential equation, is the same. So what is if you write it in the system of equation form, then this is x1 plus half x2 is equal to 0, and x2 is equal to 0, and x3 arbitrary,
Yes, sir.
no condition.
So we get one solution, sir.
Yes?
We get one solution, sir.
No, yeah, I'm doing some mistake also. Yeah, you can also further reduce it 1 0 0 0 1 0 and 0 0 0. So x1 is 0 actually, x2 is 0, and x3 is arbitrary. So the kernel of A plus I is equal to 0 0 x such that x is in R. So you may say that it is generated by 0 0 1. This is a one-dimensional subspace.
Yes, sir.
I think I am correct now. Now we can calculate the kernel of. Yeah, I'm in lack of time. Let me. Yeah. Now the kernel of this. Kernel of this. So this is those x in C3 such that a minus 2i x is equal to 0. So a minus 2i is minus 1 1 0 minus 1 1 0 minus 1 4 minus 3, and we will solve it, we will reduce it, system of equation. When we will reduce it, see, these two rows are same, so we can do 1 1 minus 1 0, or okay, no problem, and this, when you subtract, it will become 0 0 0, and this is minus 1 4 minus 3, and when you will reduce it again, you may add it. So this is 1 minus 1 0 0 0 0 and 0 3 minus 3, like this, and that you can further reduce 0 3 minus 3. This is 1 minus 1 0 0 0 0 0 1 minus 1, and then you can make this entry to be 0. So this is 1 0 minus 1 0 0 0 and 0 1 minus 1. So what will be the solution? If we will change it into the system of equation, then the solution will be x1 is equal to x3 and x2 is equal to
X3.
x3 again. So the solution, the value of the kernel of this system of equation, kernel of a minus 2i is equal to x such that x belongs to R. So this is generated by single vector 1 1 1. Do you agree?
Yes, sir.
So you have
Yes,
only
sir.
linearly independent eigenvector. So this matrix is not diagonalizable. So what you need is that you need to determine the Jordan Canonical form for this matrix. So what we will do is that now, because of lack of time, I am just writing the calculation which you can do by yourself. We will determine the kernel of a minus 2i, and this turns out to be the set of vectors of the form x y y such that xy belongs to R. Okay, so there are two vectors through which it is generated. One is, you may say, 1 0 0, and the another vector is 0 1 1 through which it is generated. So it has dimension 2. Okay, but how to determine the Jordan basis? Jordan basis means you will take one vector from here and take its image. So a minus 2i, you will take its image, the image of this vector under this. So you will get minus 1, minus 1, minus 1. So the Jordan basis will be so what we will do is that we will take one vector to be this and another vector to be this. Here we have got two vectors, 1 0 0 0 1 1. Okay, but now I will replace one vector by minus 1 minus 1 minus 1. So we have, and this is because image, so we will write it first. Whatever I am saying is because of the calculation which we have done yesterday. These are from this basis kernel of a minus 2i, and there was one more vector from this kernel of a plus I, and that was 0 0 1. So I will write 0 0 1 here. So I will write 0 0 1. So this is the Jordan basis on which that canonical form you will get. So how to write a matrix P? The matrix P will be nothing but put these vectors in the column. So the matrix P will be minus 1, minus 1, minus 1, 1, 0, 0, and 0, 0, 1. This is the matrix P. So what we have determined is that we have determined P, A, P inverse is the Jordan form. And the Jordan form was, क्या था Jordan form? 2, 1, 0, 0, 2, 0, and 0, 0, minus 1. So now, what is the rest thing which we have to do? We have to determine the exponential of this Jordan matrix. So the exponential of this Jordan matrix J, let me call it J, JA into T. T is the extra term. So this is E into T, and we will break this matrix into two parts. One is diagonal matrix minus 1, and plus another is 0, 1, 0, 0, 0, 0, 0, 0, 0. Okay, and this matrix, if you will see, this matrix is an nilpotent matrix of index 2. So its Jordan canonical form will turns out to be e to the power, sorry, this is a diagonal matrix. So this is e to the power t 2 2 2 into e to the power t and 0 1 0 0 0 0 0 0 0. Okay, so when you will solve it, this is e to the power 2t, e to the power 2t, e to the power 2t, and you know how to determine this, the Jordan.
So last one will be e to the power minus t.
Oh yes, yes, you are right.
Yes, sir.
Let me correct it. This is e to the power minus t. Minus 1 minus t. And this matrix is 0, t, 0, 1, because I add identity plus this 0, 0, 0, 1. So you can calculate it and you will get this thing. Okay. So this is your, you will just multiply these two matrices and you will get e to the power 2t, t times e to the power 2t, 0, 0, e to the power 2t, 0, 0, 0, e to the power minus t. This is the Jordan form of this matrix. Now you have a matrix P. We have determined this matrix P to be minus 1, minus 1, minus 1, 1, 0, 0, and 0, 0, 1. And you can calculate its inverse, which I have calculated. This is 0, minus 1, 0, 1, minus 1, 0, 0, minus 1, 1. And then you can calculate e to the power 80. What is e to the power 80? This is P inverse e to the power j t p. Okay, and when you will calculate it, finally you will get, after all these products, let me write, what will you get is that, so you verify it, e to the power 2t minus t e to the power 2t and t e to the power 2t 0 minus t e to the power 2t e to the power 2t plus t e to the power 2t e to the power 2t plus t e to the power 2t minus e to the power t 0 e to the power minus t and here minus t e to the power 2t, and these three column vectors are the linearly independent solution of this system of equation. So you may make its linear combination, alpha 1 times first column, alpha 2 times second column, alpha 3 times the third column, and that will give you the general solution. Yes, that's what I want to tell you. If you have any query or any question, and this is one application of this Jordan Canonical Form.
Sir, can we find this topic in that Blitz book, sir?
Yes, in the Blitz book it is given, but matrix exponential you can see in the book of Artin algebra. And the facts which I have stated is from the book of Artin algebra. Artin algebra. Michael Artin, book of Michael Artin, very famous book, algebra. And the copy which I have is from the PHI publication.
Sir, can you go the previous slide where you have calculated the kernel of a minus 2i
Yes,
square?
I can go.
Yeah. Here you have written, yes, that's a minus 2i kernel of, here you have written a by sir. And last, why is for there, sir?
No, see, I have not done the calculation here because of the lack of the time. You will do the same calculation as we have done here, and then you will get the answer.
You mean, sir, you have calculate and the right vector of the part lies in the kernel of a minus 2i square.
Yes.
Yeah, okay, sir. Okay, thank you, sir.
I have calculated it before the class, and because of the lack of time, I have not calculated it here before you, but you can check it.
Okay, sir.
Okay, and now the Jordan basis, the condition for Jordan basis, the another vector should be an image of previous vector. So I take one vector from here and take its image. So I take these two vectors. One is image of another, and then make
Sir,
a Jordan
here,
basis.
sir, here in the kernel of a minus 2i square, we have got two vectors and two
Yes.
basis vector, and you have take any one of that, any one of these, and take the image of that vector.
Yes. And the condition is
And these
that that should not be inside this kernel of a minus 2i. And I saw that this image, that should be inside the kernel of a minus 2i, and that is there. So it works. I take its image. See, in the Jordan basis, what happens? Its image should go to here. Second vector image should go to first. That then and only then you will get this matrix.
Okay, sir.
Okay, so go into the calculation and do it. And this is a application of Jordan Canonical Form in the case of system of linear differential equation with constant coefficient and homogeneous. Okay.
Okay, sir.
Any other question if you have, then please ask.
Sir,
Yes,
sir,
sir.
how can I get this video link, sir? Today's.
I will upload and send you the link.
Okay, thank you, sir.
Okay, if there is no question, then let us have a break of 5 minutes. We will meet again at 4:05 with our new speaker, Dr. Brajesh Kumar Sharma, sir, from University of Allahabad. नमस्ते सर.
नमस्ते विवेक.
Yes, let me introduce Dr. Brajesh Kumar Sharma from University of Allahabad. Dr. Sharma is a good researcher. He has several research papers. He has depth of knowledge, and I am also a student of him. Today he will speak on non-negative matrices. Am I correct, sir?
Yes.
So I invite Dr. Sharma for his speech. Yes, sir.
Okay. Thank you, Vivek. First, I would like to thank organizers of this workshop to speak. So I will speak on non-negative matrices. So matrix is said to be non-negative if all its entries are non-negative real numbers, meaning we are considering matrices of real numbers. So let me share the screen. So So, so we are considering the matrices A, a real field, and we say A is non-negative if all its entries are non-negative. And likewise, we say positive matrix if all its entries are positive. So in general, a matrix with real entries may not have real eigenvalue. So for example, this matrix 1 minus 1. So its characteristic polynomial will be x square plus 1. So it doesn't have real eigenvalue. A remarkable result is proved by Perrin. So O Perrin in 1907. So the theorem is this. So let A be a positive n cross n matrix. Then it has a positive eigenvalue. So first A of y is equal to lambda naught y. So A is an n cross n matrix. So for some where lambda is positive, and also all coordinates of y are positive. So y is an element of Rn and y is positive. So this means all coordinates of of y are positive. And not only that, second, it says that it may have complex eigenvalues also. So this is the largest, this is maximal. So yeah, this lambda naught is maximal in modulus. It means that, so that is for any eigenvalue mu, lambda naught is greater than or equal to modulus of mu for any eigenvalue mu of A. And this is, first of all, it asserts that there is a positive real eigenvalue. If you have a matrix with whose all entries are positive, then it has a positive eigenvalue, positive real eigenvalue, and it is maximal. And this eigenvalue is algebraically, its algebraic multiplicity is 1, and also its geometric multiplicity is 1. So it's so geometric, the geometric multiplicity of lambda naught is 1. Means it's the dimension of this eigenspace V lambda naught, let's say this is 1. And any positive eigenvector and any positive eigenvector of A corresponding to any eigenvalue, corresponding to any eigenvalue of A is a scalar multiple of Y. So this is the theorem proved by Operan. Is the statement clear?
सर इसमें लैम्डा नॉट एक ही मिलेगा?
हाँ, यस, एक मिलेगा जो मैक्सिमल होगा, तो एक ही यूनिक हो गया वो। मैक्सिमल लैम्डा नॉट हैज द प्रॉपर्टी, इट में है many real eigenvalue, it may have complex eigenvalue, but this says that there is a positive real eigenvalue, there is a positive real eigenvalue, वो यूनिक हो गया और मैक्सिमल है,
मॉडुलस।
हाँ, मॉडुलस मैक्सिमल, ये मॉडुलस, ये it may have complex eigenvalue also, but their absolute value is less or equal to lambda naught. This is the maximal among all eigenvalues.
Yes.
Now the statement clear?
Sir, here y is in 4 statement.
Yes, y भी एक मिलेगा। देखिए, ये थ्योरम कह रही है कि एक लैम्डा नॉट मिलेगा आइगन वैल्यू, और उसके करस्पॉन्डिंग अगर आइगन वैल्यू पॉजिटिव है तो ये जरूरी नहीं है कि जो आइगन वेक्टर्स हों उनके कोऑर्डिनेट्स भी पॉजिटिव हों। तो दोनों स्ट्रांग चीज है। पहली बात, आइगन वैल्यू मिलेगी जो पॉजिटिव रियल नंबर होगी, फर्स्ट थिंग, एंड सेकेंड थिंग उसके करस्पॉन्डिंग जो एक आइगन वेक्टर मिलेगा जिसके सारे कोऑर्डिनेट
Yes.
पॉजिटिव होंगे, सारे कोऑर्डिनेट्स पॉजिटिव हैं, ये है। और इसकी ज्योमेट्रिक मल्टीप्लिसिटी 1 है, और कोई भी पॉजिटिव आइगन वेक्टर है। पॉजिटिव आइगन वेक्टर मींस एन आइगन वेक्टर ऑफ ए whose all coordinates are positive, तो वो स्केलर मल्टीपल होगा y का। Yes, now the statement clear?
Yes, sir. That means y is the eigenvector corresponding to eigenvalue lambda 0.
हाँ, y is the eigenvector corresponding to lambda.
Yes, yes. Okay.
Hello.
So,
Sir, I have a question. Sorry to interrupt you. Sir, hello.
yes,
Yes, sir. I have a question. If A is any matrix, right, sir? And
Yes.
we know that if all the column sums and row sums of a matrix are equal, then it is an eigenvalue of A. Right? Sir?
yes, please repeat.
Yeah. If A is any matrix, arbitrary matrix, and such that all its column sum and its row sums are equal, then it will be an eigenvalue of A. There is a result. And my question is that also there is a result, and that sum will be the maximum value of that maximum that sum will be the maximum eigenvalue. Means that
Yeah, there may be many.
Yeah.
In fact, we know that if we have any norm, suppose if you have any matrix norm, and if lambda is eigenvalue of A, then mod lambda is less or equal to norm of A. But
my
here,
basic question. Yes. So my basic question is that if A is any matrix such that is all row sum and column sums is equal to say sum alpha, then
Yes.
there is a result that any eigenvalue, its absolute value will be less than equals to alpha. And my question is, how is that particular related to this theorem? Am my question making sense to you, sir?
okay. So first see the importance of the theorem. A matrix may not have real eigenvalue.
Obviously.
Yes, may not have real eigenvalue.
Yes,
But
sir,
this shows that if A is positive, all its entries are positive, then it has a positive real eigenvalue,
Okay.
right? And not
Yes,
only that, corresponding to that, there is a eigenvector, all whose coordinates are positive.
Okay.
There may be many results. There are many results which says what are the bounds on eigenvalues. Okay? In which interval the eigenvalues lies, that are the thing.
So
But
using this result
this
1 and
theorem
2,
is proved by
so-
Paran.
yes. So using this theorem, that the theorem we have mentioned, using these two conditions of 1 and 2, can we say that maximum means absolute sum of all the rows or column of a matrix will be lambda naught? Is it possible to say that? If A is a matrix and you are saying that if lambda naught is a maximal, means lambda naught is the maximum eigenvalue. And is it possible to say that using this condition 1 and 2?
No, we
that
can. So this is, we
because
have a row
somewhere-
norm and column norm of a matrix.
Yes, sir.
So absolute value of lambda will be less or equal to the sum of maximum of sum of rows.
Yes, yes. Sir.
Yes, that can be introduced.
Okay.
So
Okay,
now,
sir.
okay. So
Okay, sure.
for example, for case of 2 cross 2 matrices, so suppose we have a matrix, all its entries are say positive. Say this is the matrix. So in case n is equal to 2, so n is equal to 2, so what will be if A is this?
It's eigenvalue, sir.
Okay, so then A, so E1, A E2. So means this first sector, this we have this first quadrant. So it will map these vectors something.
Yes, sir, in different directions.
Okay, so it maps first quadrant to inside the first quadrant.
Yes.
So if S is the first coordinate, then S contains AS. Okay. And then again we apply A square S. So sectors and then sectors inside it goes. So it comes out that their intersection of A to the power RS or say positive integer, this comes out to be a half line. So that guarantees a existence of positive real eigenvalue and existence of eigenvector whose coordinates are all positive.
Okay,
This
sir.
is the in case of 2, but there are combinatorial proofs. There are many proofs of this. There are many combinatorial proofs, but in general dimension, there is a proof which uses one theorem, very important theorem, known as this Brouwer fixed point theorem. So, Brouwer fixed point theorem. So this says that statement is this. So if so let S be a closed bounded convex subset of Rn, Euclidean space Rn, and we have a self map. So and let f from S to S be a continuous function, from S to S, then it has a fixed point. So then f has a fixed point. So that is, there exists x in S such that x is equal to f of x. So convex means if you take any 2 points, then the line segment joining any 2 points in S also lies in S. So for n is equal to 1, this is intermediate value theorem. So because any closed convex bounded subset of R, this is closed interval. So this is a bounded closed interval. This is closed interval. And we know that intermediate value theorem, that using intermediate value theorem one proves that any continuous map, so any continuous map f from AB to AB has a fixed point. For higher dimension, we have to use this algebraic topology concept of fundamental group. So we shall use this theorem to prove the existence of positive real eigenvalue whose all coordinates are positive. So for this, take a positive matrix, n cross n matrix. So we have to consider a subset, convex subset. So we take this convex subset S is equal to, so we are writing the elements of Rn as column vectors, the Xn transpose column vectors. So we take each coordinate is positive, xj is greater or equal to 0 for j 1 to n, and then sum of xj 1 to n, all this to be 1. We say this is geometric n simplex. So we say geometric n simplex. So this is a closed bounded convex subset of Rn. So this is subset of Rn. And now A is positive. A is positive means all entries of A are positive. So if we have a vector, some x in S, this implies Ax is also in S. So, and also, if x is in S, then not all coordinates are 0. If x is in S, this implies not all, x is non-zero. It has to be non-zero. So, because the sum of all coordinate has to be 1.
Sir,
Yes.
sir,
Yes.
why x is in S? Because since x is positive means all coordinates are positive, and here x1, x2 of x
Yes.
transpose is positive, then closure
Yes.
property holds. Then
Yes.
okay,
If
sir.
A is positive means all entries of A are positive.
Positive. Yes, sir.
And if x is in S means its coordinates are non-negative.
Yes, sir.
And one of coordinate must be non-zero, positive, because this
Yes, sir.
sum is equal to 1.
Yes, sir.
So positive and multiply first row, first column, so we will get non-zero, because
Yes,
all
sir.
entries
Means,
of A are non-zero.
sir,
So the
here
sum
x
will
is
go.
multiple of both vectors, right?
This is the A is n cross n matrix, and
Yes,
x we
sir.
are taking as a column vector, means as
Okay, sir.
n
Okay,
cross
sir. I
1
got it.
column vector.
Okay, sir.
X has n cross 1 column vector, so result will be this n cross 1.
Yes, sir.
So it
Yes, sir.
has
I
to be
got
this.
it, sir.
Yes.
I got it,
X
sir.
non-zero, so x is non-zero. So x is, of course, since x is greater or equal to 0, it means all its coordinates are non-zero, and at least one coordinate has to be positive. Okay. So what would we have to define a function? We have to define a function. So so sum of coordinates. So sum of coordinates, it means sum of the coordinates of Ax, j or I, whatever. So j from 1 to n. So this is positive, right? Because Ax is positive.
Yes, sir.
So now we define a function f from S to S. So f of x, define this to be, so we invert this. So sum Ax j, sum over this, and then Ax for all x in S. So this is a continuous map from S to S. So by the Brouwer fixed point theorem, and for the proof of that, you have to see use the algebraic topology tools. So there is a fixed point. So by Brouwer's fixed point theorem, fixed point theorem, we have, it has a fixed point. So there exists y in Rn, y in S, Rn. So
Sir,
yes,
here why use the algebraic topology? Because only use the fixed point theorem we get a y in S. But sir, algebraic topology
look,
why use?
for the proof of Brouwer fixed point theorem.
Okay, sir.
Okay. Look at, see, first in the, for n is equal to 1 case, we have seen the any closed bounded convex subset is the closed interval, right?
Yes,
And
sir.
there we have
But sir,
intermediate value theorem. So we
but sir, this is true for only Rn. R.
only Rn
Yes, sir.
for subsets of Rn.
Yes, sir. Yes, sir.
So for two means if you have any map from B2 to B2.
Yes, sir.
So B2 is the closed disk.
Yes, sir.
And
In
it is continuous, it has a fixed point. So there you
yes,
have to
sir.
use, you can get
Yes,
the
sir.
proof in Mankrej's book also,
Yes, sir. Yes,
topology
sir.
by
Yes,
Mankrej,
sir.
that
Yes, sir.
uses
Yes,
that
sir.
S1 is not a retract of B2,
Yes, sir. Yes, sir.
not a retract of B2. Okay, so that will
Yes.
use not the retracts, and the fundamental group also used. That fundamental group of S1 is Z, fundamental group of B2 is trivial. So, but again you have to go next 3-dimension general nth dimension. Then again you have to use the this algebraic topology tool. So by Brouwer fixed point theorem, here we are using. So there exists y in S such that a f of y is y, right? So this means a of y is equal to, so that is a of y is the sum of a x j from 1 to n of y, and take lambda naught. So we take lambda naught is the sum a x j 1 to n. So it is the positive. So this is positive. And now A is a positive matrix. So, and Y is a non-element in S. So all entries of Y are positive. So Y is also positive. Because AY is equal to Y. So this proves that there is a existence of positive real eigenvalue and an eigenvector all whose coordinates are positive. Now is it clear?
Yes, sir.
Yes, up to this point clear?
Yes, sir. I have one doubt here.
Yes.
We define a function from B2 to B2. Then here, sir, here B2 is a subset of Rn or R2. Means if R2, then all
B2
taking
B2 is subset of
B2.
R3. B2
R3
is
means
subset
third
of
coordinate.
R3.
Third coordinate is 0, sir.
B2 unit. So this is the 2 disk. So in R2.
Okay, sir. Okay, sir. Okay, sir.
Unit 2 disk. So its boundary is the S1, one less.
And S1, sir, what is
Circle,
S1?
circle, unit circle. So this is a disk.
Yes, sir.
Its boundary is this one.
Okay,
So
sir.
this there is also combinatorial proof, many proofs of this, but one proof is using this Brouwer fixed point theorem. And then one uses that it's geometrically simple, its dimension of its maximal. So let again see the theorem so that this is the theorem. So matrix with positive entries, all entries are positive, has a positive real eigenvalue and eigenvector, and its maximal geometric multiplicity is 1, and any positive eigenvector corresponding to eigenvalues of A is scalar multiple of Y. So I'm not going to prove the other. So you can see this famous theorem proof in any book or literature. So now there is generalization. Frobenius generalized this result for the matrices with non-negative entries. So non-negative entries, so matrix A is non-negative. So we cannot, so there is a condition on A. The same result holds, but we have to assume one condition that A is irreducible. A is irreducible. So this theorem is generalized by known as Perrin-Frobenius theorem. Frobenius theorem. So it says that let A be a non-negative irreducible. So we will define what irreducible means. Irreducible matrix, n cross n matrix, irreducible n cross n matrix. So of course A is an M&R. So then there is just a positive real eigenvalue. So just I will define what irreducible means, but so then there is a positive real eigenvalue. There is a positive eigenvalue lambda naught of A, which is maximal with positive eigenvector, with positive eigenvector. Why?
Because A is irreducible matrix.
Just I will define it. Wait 1 minute. So positive eigenvector and
Yes.
lambda naught is maximal, and again same result, it is maximal modulus. So and mod of mu less or equal to lambda naught for any eigenvalue mu of A, and it is algebraically simple. Lambda naught is geometrical simple, its dimension is 1, is algebraically simple. Means it's is the only one times repeated. And again, any vector, and not only that, if also if lambda 0, lambda 1, lambda k minus 1 are eigenvalues of lambda of A such that their modulus is lambda naught, such that lambda j is equal to lambda naught for j 1 to k. So then they satisfy then lambda, these satisfy this equation lambda to the power k is equal to lambda naught to the power k. So means they are the kth root of unity. Means if you know one eigenvalue, then all eigenvalues whose modulus is lambda naught, so they are the, means lambda naught, the eigenvalue will be lambda naught e to the power 2 pi I by k, lambda naught e to the power 2 pi I by 2 k, and like this. They satisfy this equation. And again, any positive eigenvector corresponding to any eigenvalue of A is a scalar multiple of Y. So again, its proof, the uses matrix games, maybe technical combinatorial proof. So this is the Perrin-Frobenius theorem. It has many applications in probability theory, game theory, numerical analysis, and economics, dynamical systems. So this theorem has many applications. So now let me define what irreducible means. What do you mean by irreducible matrix? So irreducible matrix means so an n cross n matrix A is said to be irreducible. Is said to be irreducible if there is no permutation matrix. There is no permutation matrix P. So we know what is a permutation matrix. The matrix which is obtained by applying a permutation of column, obtained by permuting its columns or rows. P such that this P A P transpose, this is the orthogonal matrix, permutation matrices. So this is equal to this A, say here 0 B D, like this, where A and B are square matrix. A, B are square matrices. So we say irreducible. So there are criterion for irreducibility.
Sir,
Yes.
and D is the diagonal matrix here.
No, this is not diagonal matrix. D is any matrix.
For any square matrix.
A and B are square matrix.
And
A
D
and
is?
B are square matrix. This is the zero matrix. This is zero. D is not diagonal. So this is.
Sir, so why we have not taken D's square matrix? Because here D is any square matrix we have to taken. Can we take?
So D may not be square matrix. Is it okay? For example, it's not true that D is square matrix. for example, you take say D is, so like for example this say 5 cross 5 matrix, so this is, we have a block 2 cross 2 and 3 cross 3. So this is 0 matrix, so this will be 2 cross 3 matrix. This will be here. Yes. So D may not be square matrix.
Sir, D will be 3 cross 2 matrix.
Yes, 3 cross 2. Yes, thank you. 3 cross 2 matrix. So D may not be square matrix. So this is the. So this means that for the eigenvalue consideration, if you want to, sorry, it's not a. It has to, it's not the same A. You have to put. It's not the same A. So some matrix A. So B, C. Some. Sorry, sir. CBR square matrices. They are square matrices, they are not the same. So for irreducible matrices, this theorem holds. And now non-negative matrices, so there is one result. So one can ask, suppose you have a non-negative matrices, then their sum product is also non-negative. Sum and product of non-negative matrices is non-negative. Simple thing. It's trivial. But one can ask, what about inverse? So there is real that so A, this is A non-negative, then its inverse. So in A inverse is if and only if A is a generalized permutation matrix. Generalized permutation matrix. Generalized permutation matrix means a matrix which have same zero pattern. In permutation matrix, each row and each column has one exactly once. But here the entries, each row and each column has exactly one non-zero entry.
Yes, sir.
Same zero pattern as the permutation matrix. Now this 0-1 matrices are important matrices. Non-negative matrices are important. So they occur in, for example, adjacency matrix of any graph of graphs. And also there is a in combinatorics system of distinct representatives. Of subsets. So they also occur there. So system of distinct representatives, it means that suppose you have a set, S is a set, say 1 to x1, x2, xn. A set with n elements. And if you have a given a subset, say S1, S2, Sm, so they are the subsets of subsets of S, non-empty subsets, of course. Then one can, so what do you mean system of distinct representative? Means a pair. So some y1, y2, ym. So we say this tuple is a system of distinct representatives for this system S1, S2, Sm. If they are all distinct, if yi is not equal to yj and yj belongs to sj. So then the question, when a system of distinct representative exists, and if it exists, how many are there? If when a system of distinct representative for a given this family of sets exists, and if it exists, how many are there? So there one construct a matrix, we say incidence matrix of system, incidence matrix of this system S1, S2, so S1, S2, Sn. So this is a M cross N matrix. So whose entry, so Aij. So this is M cross N matrix. So Aij is 1 if Xj belongs to Si. Otherwise it is 0. 0 if Xa doesn't belongs to S. So this is the incidence matrix, M cross N matrix. Likewise, we have a determinant. There is a notion of permanent. Permanent of a matrix. So how it is defined? So we define like this: permanent of a, in determinant we take the signed sum, put some sign, but here we do not put sign. The product ai sigma I and I is 1 to m, and sigma varies over all injective maps from 1 to m to 1 to n. This is called permanent. So it has similar properties with determinant. In determinant, we have m is equal to n. Determinant is for only square matrices, and we put here sign of sigma also. But in permanent, signless. So the result is that this I want to state that the system has SDR. So system S1, S2, Sm has SDR. So of course, because they are the subset of n element set, so m has to be less or equal to n if and only if the permanent of A, so permanent of its adjacent matrix is positive, and the number of SDR and is equal to the permanent of the configuration. So this is equal to permanent of A. So the non-negative matrices, very important, they have very rich structure, theory, and many applications. So I wish to stop here. If you have any question, you can ask.
Sir,
Yes.
sir, can you give one example of generalized inverse matrix?
One example of
Means, sir, can you give one is just so example of generalized inverse matrix? Like
generalized inverse matrix. So
and
that definition,
generalized inverse matrix, sir.
that I am not clear about what is generalized inverse, how it is defined.
Matrix.
Generalized.
Generalized inverse
There is a
matrix.
generalized inverse of the matrix. So I am not
Yes,
clear
sir.
about that.
Okay, sir.
So I hope you must have got the result that Homogeneous theorem,
Yes, sir.
a matrix with positive real entry, all its entries are positive, has a positive real eigenvalue. And it has an eigenvector, all its coordinates are positive.
What is mean by SDR short form?
Yes, yes, system of distinct representatives. System of distinct representative, because non-negative matrices occurs in many situations. So this is the one where non-negative matrices occurs. In graphs also, graph theory, there is adjacency matrix, incidence matrices, there are also 0-1 matrices. If you take weighted graph or the graph with multiple edges between two vertices, there also you get non-negative matrices. So that's why I just wish to state this theorem.
सर
Yes.
नॉन नेगेटिव मैट्रिक्स एंड पॉजिटिव मैट्रिक्स, ये जो टर्मिनोलॉजी है, ये अलग अलग नाम है या सेम है सर? नॉन
नेगेटिव का मतलब वही
नॉन नेगेटिव एलिमेंट होंगे और पॉजिटिव,
हाँ, यस, रियल मैट्रिक्स
और पॉजिटिव
in non-negative some element may be zero, but when we say positive means
तो आइगन वैल्यू का होगा. जब हम पॉजिटिव मैट्रिक्स की बात करते हैं तो हम बात करेंगे इसके आइगन वैल्यू पॉजिटिव होंगे, ऐसा सर?
आइगन वैल्यू पॉजिटिव होंगे नहीं कह सकते, एक आइगन वैल्यू होगा जो पॉजिटिव होगा और मॉडुलस में सबसे बड़ा होगा. इट मे हैव कॉम्प्लेक्स आइगन वैल्यू आल्सो, इट मे हैव नेगेटिव आइगन वैल्यू आल्सो.
Sir, please recall what is algebraically simple element in a field.
अच्छा, algebraic simple is, suppose you have a matrix.
Yes.
It's a very simple thing. A matrix, say M and C, algebraically closed field we are taking. Look at its characteristic polynomial. So characteristic polynomial of A, that is a determinant of xi minus A, yeah, A minus xi. So this will be the product of, because C is algebraically closed, this will be product of linear factors, means x minus say lambda 1, say k1, x minus lambda 2, k2, x minus lambda r, suppose it has r eigenvalues kr, right? So then this power k1, so kj is called algebraic multiplicity. Algebraic multiplicity of eigenvalue lambda j, means the maximum power of x minus lambda, lambda j, which divides characteristic polynomial of A. That is the algebraic multiplicity. And geometric multiplicity means the dimension of the corresponding eigenspace.
Yes, sir.
Yes.
But algebraically simple, what is which
That
eigenvalue
means
is said to be there?
multiplicity is 1.
Okay.
Yes, algebraically simple. Yeah, geometrically simple, we say its dimension is 1.
So any another question, then you may ask. और किसी को कोई क्वेश्चन हो तो पूछ सकते हैं.
Sir, the proof of these theorems in which book?
Maybe you are asking for differences. Yes.
मुझे सर सबका रिकॉर्डेड वीडियो अपलोड कर दीजिए यूट्यूब पे.
Okay.
हम्बल रिक्वेस्ट.
We have not recorded all the videos. This is my mistake, and we have started recording from the lecture of Dr. Vipul. So after that, I will upload everything.
Yes.
Okay. So if there is no question, then this is time to thank our today's speaker, Dr. Brajesh Kumar Sharma sir. He has introduced us with non-negative matrices and he gives several examples and results related to it. So thank you very much, sir.
Thank you, Vivek.
This is the
Thank you,
time.
Swapnil. Namaste.
So
Okay, so
yes, tomorrow there will be one lecture by Professor Ramjilal, and after that there will be valedictory. And if any one of you want to say anything in that valedictory session, then you can give your name through email to me. You can share your experience.
Tomorrow will be the last day of the workshop, sir.
Yes, tomorrow will be the last day of the program.
Yes.
One lecture by Professor Ramjilal, special lecture, and then after that there will be valedictory session.
Only one lecture.
Only one lecture, and then another one will be the valedictory session.
Okay, sir. Okay.
Okay, thank you everybody, and let me close the meeting now. Thank you, sir, again, and thank you, Dr. Swapnil, for joining us. Thanks to everybody. Thank you.